Hello, my name is Ivan Taylor, and I'm from Ontario, Canada. And this is a presentation that I gave to the African Space Leadership Institute on July 29th, 2026. It's entitled Systems Thinking and System Dynamics for Space Leadership. And my company is called Policy Dynamics, and I'm in Ontario, Canada. So the session objectives are to understand systems feedback and unintended consequences, to distinguish causal loops from stock and flow models, to follow a disciplined system dynamics process, to examine population growth and space debris models, and to understand how AI can support model development and apply systems thinking to space leadership. So systems are defined by purpose, interaction, and feedback. So a system is a set of interconnected elements. Its structure produces behavior over time. Feedback creates intended and unintended consequences. So every system has intended behavior and unintended behavior. Sometimes the unintended behavior is good, sometimes it's bad, and system dynamics can help you see the unintended behavior that may not be obvious at first. And system boundaries are important because you can't model everything. You have to put a boundary on the system that you're modeling, and it's based on the problem that you want to examine. So now we have this idea of feedback thinking. So linear thinking is where A causes B and B causes C. So that's a linear relationship, and it's cause and effect. And feedback thinking is where A causes B and B causes C, and then C causes A. So the effect is actually the cause. So it's a loop. So causal loops describe the feedback structure, and stock and flow models take those causal loops and build quantitative models to simulate the behavior of the system over time. So feedback explains why interventions can produce delayed, indirect, or unintended results. So there's two types of modeling in system dynamics. One is qualitative models, which are basically causal loop diagrams, and they involve links, polarities, and feedback loops. And then there's quantitative models, which are stock and flow diagrams, and they involve differential equations solved using numerical methods, units of measurement, and parameters. Okay, so causal loop diagrams describe the feedback structure, and the variables are connected by causal relationships. And there's reinforcing loops amplify change, and balancing loops resist change. And the loop structure explains behavior over time. So link polarity shows how the variables change together. So they can move in the same direction. So in this case, we have an idea that an increase in national investment will increase technical achievement. So they move in the same direction. Or they can move in the opposite direction. So in this case, budgetary strain could increase and lead to a decrease in national investment, which is represented by the O, which is the opposite direction. And then we have delays, and this is where, for example, technological achievement with a delay can lead to international prestige, and these move in the same direction, but there's a delayed reaction there. And reinforcing loops amplify change and balancing loops resist it. So here's a small model with a balancing loop and a reinforcing loop. And we see that if we start with national investment here, we see that increases in national investment lead to increase in mission experience. And increases in mission experience leads to increases in technical achievement. And then after a delay, an increase in technical achievement after a delay leads to international prestige. And increases in international prestige can lead to more national investment. So that's a reinforcing loop labeled R1. And then we have a balancing loop. So national investment is not unlimited. So the more national investment there is, the more budgetary strain there is. However, the more budgetary strain there is, the less national investment there is. So increases in national investment lead back to decreases in national investment with a balancing loop, and increases in national investment lead to circle the loop of reinforcing side and increase international investment. So the reinforcing loops change generates more change, and in the balancing loops, change triggers a corrective response. And delays may mean that the system responds, but that may arrive too late. And then you can put many feedback loops together, and they can produce a model of a system. Then you can determine the behavior of the model. Here's a larger version of that stock, and it's causal loop diagram. So we have the original two loops, R1 and B1 over here. And then we have an additional R2 loop here, R3 loop here, and B2 loop here. And so this is a model of space leadership that I put together a couple of years ago. Now, system dynamics connects the feedback structure to behavior over time. So it begins with a dynamic problem, a policy issue, and it represents feedback using causal loop diagrams, and it converts the important structures in the causal loop diagrams into stocks and flows, and it simulates how the system changes over time. Then we can test policies to change the system and test those changes before they're implemented. And here's a small example of a stock and flow diagram, a quantitative model. And this is what's called a goal gap model. And we have a desired stock here in the upper left-hand side. We have an initial stock over here in the upper right-hand side. We have a stock represented by a box, which is actually the state of the system or the accumulation of some kind of material. And we have a flow here. So we have an inflow, or in this case, or possibly an outflow if the flow is negative. And then we have a time to close the gap. So basically, we start with an initial stock. We have a desired stock. We look at the difference between the current stock level and the desired stock level, and we get a gap. And then over time, we create a flow to close the gap between the desired stock and the actual stock. So over time, that gap closes. So this is a goal gap model. It involves one stock and one flow and three parameters: this initial stock, the desired stock, and the time to close the gap. Those are in capital letters. And then auxiliaries, the gap is an auxiliary calculation, and it's all in all small letters. And then we have connectors, which are those blue arrows that show the connections, and those are also inputs to the equations, show the inputs to the equations in the auxiliary variables. So stocks are the state of the system, and they record the system's history. So it's, as I said, it's the behavior over time that's important here. So how do you translate a stock and flow model into equations based on a diagram like this? So we have, let's say we start with an initial stock of 100 units, and we have a desired stock of 200 units. And then we measure the gap between the desired stock and the current stock level, and that's the gap. And then we have an inflow, which is the gap divided by the time to adjust. And then we take, as I said, a numerical integration of the inflow over time, where we started with an initial stock level. So how does numerical integration work? Well, it works based on walking through time, one step at a time, and calculating and updating the values at each time step. So here's a table of results from the model with a time step of 1 month. So at time 0, we have 100 units in the stock. So that's the initial stock level. And then we have 8.333 units per month going into that stock in the first month. And that's based on closing the gap. That's the amount of gap divided by the time to close the gap. And that's the amount of flow that goes into the stock in the first month. So at the end of the first month, we have 108.333 units of stock. And then we calculate the flow for the first month, for the second month, I guess, from month 1 to month 2. And we see that we have 7.63889, and that's the flow into the stock between month 1 and month 2. So at the end of month 1, at the end of month 2, we have 115 units of approximately 116 units of stock. And then we calculate the next time step, which has a flow, and add that to the stock. And basically the stock value at any point in time is the previous stock value plus the inflows minus the outflows times the time step. So in this case, we have only one inflow. So we have a stock level, and we then add the flow level in the previous time step, and then we multiply that by 1 because it's a 1-month time step. And we can look at the results that the gap declines. As I said, you can see the gap declining and the inflow slows and the stock reaches equilibrium. And you can see that here in this graphic. So this is a goal-seeking structure. So we can see that this produces convergent behavior. So the red line is the stock over time, starting at 100 units and reaching the desired level of 200 units over a period of months. And the gap starts at 100 units, which is 200 minus 100, the current level, time minus the desired level minus the current level is the gap, starts at 100, and over time the gap decreases as the stock gets closer and closer to the desired level. And the gap relates to the flow. So now we can say that the stock approaches its target gradually because the corrective flow declines with the gap. I follow a disciplined modeling process that connects problems to policies. And this is the instructions from the Systemdynamics Society on the way to build and document models. So you start with a dynamic problem or a policy issue or some kind of problem. Then you develop a reference mode, which is a set of historical data showing the behavior over time, the historical behavior over time of the important aspects of the problem. And then we develop a dynamic hypothesis to explain that reference mode based on feedback. So that's a causal loop diagram. Then we build a quantitative model based on that dynamic hypothesis, which is a stock and flow model. Then we test, validate, and calibrate the model. And to calibrate the model, we match the model output to the reference mode to get the parameters of the model. Then we conduct sensitivity analysis on the parameters, and we start to compare policy scenarios. Then we can draw conclusions and recommendations. And you can see how this process can lead you to a good documentation of a model and has all the aspects that you need for a good publication of a journal article based on a system dynamics model. So we have an introduction in the problem. We have some data collected. We have a method involving a dynamic hypothesis and a quantitative model. We test and validate. We conduct sensitivity analysis, and then we produce the scenarios, which is the results. And then we have a discussion and conclusion. So we have an introduction, literature review, method, results, discussion, conclusion. All those aspects go into a journal article. So AI supports my modeling process. So this is what I've been doing lately. I have AI support me in this 8-step procedure. However, I'm the boss and it's the worker. And so as I've read in a lot of different places, AI is going to turn all of us into managers or supervisors, and AI agents will be workers, and we will be directing them and evaluating their work and basically being the boss. And I take this very seriously, as I said. So I spend a lot of time working with ChatGPT in my case, and we work together as a boss and a worker. So I get ChatGPT to produce text files as raw output. And then I take that raw output and I turn it into a Vensim software. And then we together work iteratively to perfect the model, because generally the model that AI produces is not perfect, and we have to make corrections to get it perfected, and that can take time. And then once it's perfected, it can help me document the model, and then we can evaluate the work for publishability, the documentation, and then we can pick a target journal, and then we can work together on a paper. But I remain responsible for the final product. So, for example, the problem definition involves asking the following questions. What is the problem? Why does it matter? Who will use the model? What dynamics must it explain? What policies will it test? And why are we using system dynamics? And that is a good structure for an introduction. And then we have the causal loop diagram. And I ask ChatGPT to generate a CLD table, which is a causal loop table, where I have rows. Each row is a loop. And the first column has the loop number. The second column has the loop name. And the third column has the causal chain. So let's try this out. Just another note is that I have just completed a book on system dynamics using Excel, and I go through this process and show it how it's used in a number of case studies. So in my introduction to system dynamics, I talk about a simple model, which is the population model, and Okay, so I'm going to ask ChatGPT to generate a CLD table or a simple population model using crude birth rates and crude death rate. Okay, so let's see what it, now I've done this many times, so it knows, ChatGPT now knows what CLT tables are. So let's see what it generates. So this looks good. So now I can take this and I can copy this into a spreadsheet, and let's go back and share my screen again. So now I have a spreadsheet. So I'm going to copy that table into a spreadsheet, and then I'm going to I'm going to then take this spreadsheet, and I'm going to convert this to a VinSim model, a VinSim causal loop diagram. So let's pull up VinSim and okay, so let's pull up VinSim and let's take the spreadsheet, and let's go here and take population, and we will cut that and put this into the VinSim software as a variable. So we have births, we have population there, and then we can go back and get the births. So then we have the births, and we put them here. And then we connect the births to the population and the population to the births. And then we put comments in. So I'll put a comment here called S, and this is going to be a little symbol for the same um, same direction, and then I'll make a copy of the S. Say no there, and I will put that here, and then I will get another comment, and I will put in R1, and this is going to be a clockwise loop. So here's the loop, and I can generate a loop diagram generally like this. Now I won't go into the whole process, but basically I'll just show you what happens in the end. So So here's the final causal loop diagram for the simple population model. And you can see the population and births move in the same direction. More births leads to more population. More population leads to more births. Higher crude birth rates leads to more birth. And then population increases lead to more deaths, and more deaths lead to less population. So this is a balancing loop, and the crude death rate, if it increases, then it increases the deaths. So this is a very simple causal loop diagram for a very simple model of population. So then I generate a stock and flow diagram. So I get the AI, ChatGPT, to build a Vensim model and output it as a text file with equations, parameters, and units. So let's go back and let's go back and go to ChatGPT, and I'm going to say generate. Oops, I got to share my screen. So let's share my screen here. Okay, I want to say generate a Vensim model based on CLV for, let's say, for Nigeria. Okay, so here's the model here. So if I can download this model and I can open it in a text file. So here's the model, and I can then take the text file and I can start building a Vensim model. So let's go back to Vensim. I'm going to close this. I'm now going to save it. I'm going to generate a new model, and I'm going to say that this. So I'm going to say that this is going to be a model of population by year. It's going to start in 2025 or 2026, I guess, and run till 2050. And it's going to go a time step of to 5 years or a quarter of a year. Well, I set that up. Then I go back to my text file, which has the formulas, and I see that this is an integ, which is integration function. So that means that population is a stock. So then I go back here and I say I have population as a stock, and therefore I have it in a box. So there's population, and so there's the population stock, and then I have an inflow of births, and I have an outflow of deaths. And I have an initial population. And I have initial population here. So I have the initial population, and then I can connect the initial population to the population, and basically now I have started the model. So I'm not going to bore you with the process. I'm going to go straight now to the final version of the model, which so I will note that. Okay, so here's the full model after I've done all the information. So now I have the full model, and first thing I do is each of these variables has units. So here's the equation. So here's the equation for the population stock. So we have births minus deaths, and our initial value of initial population, and the units are person. And then we have a flow of births, and this is the population times the accrued birth rate divided by persons per thousand, and that's in persons per year. And so anyways, this is now, the equations are all input. So then I will check the units. So let's check the units, and the units are okay. That's an important check to make sure the equations work. And then I can run the model. So let's run the model now. And we can see that the population is increasing. This is for Nigeria. So over the next 25 years, we can expect the population to go from 230 million people to about 400 million people the next 25 years. And it's growing exponentially. So now the next thing I want to show you is how I convert this to a Excel spreadsheet. And so I have this now. I take this and I go to Excel. And let's go to Excel. And I'm going to start a new file. And I paste the equations down here. And then I take those equations and I open up another file like this, and I take the equations and I transpose them, and then I start cleaning it up. So now I'm going to insert some columns, and I'm going to start building the model. So I'm going to say this is the parameter, this is the value, this is the units, and this is a comment, and this is time. And then I start building the model from the equations. So I have bursts in this column. So let's wrap this. Okay, so now we can see we have time here. We have bursts, and this is an equation. So I will cut this equation and put it in this second cell. And let's do this again. So I'll cut the units, and I'll put this in the second row. So I'll have all the units in the second row, and then I'll put the equation in the next row, and then I will have the comment. I'll delete the comment for now. So basically now I have the first formula, and then I have the birth rate. So this is going to be, let me cut this and put it here. And then I will delete the cells here. And then I have the death rate. So I take these cells and I put them here. And then I have the deaths. So I take the units and I put the units here. And I take the equation and I put the equation here. And then I'm not going to use the final time, so I'm going to delete that. I'm going to delete the final time because that's going to be controlled by the spreadsheet. And then I'm going to have the initial population. So this is the initial population, and I will put that here. And then I'll have the initial, this, and then I'll take the initial time and I'll put that here. And then we'll see. And then I will and anyways, so this is basically all I need for now. So I'm not going to do any more with this equation. So I guess I do need the population. So I'm going to delete these columns, and I'm going to calculate the this cell, put it here, and then put the equation of the update here, and put that, sorry, I'll take the initial population, and I'll put that here. And then I'll take the equation of the integration and put it here. And then I'm going to, that's all I'm going to do for now. The other stuff is just accounting. I guess I need the time steps, so let's delete these cells, and I'll have the times. Oh. So I'll time step in here. Okay, so now I have everything I need. I have the births, the deaths, and so now I'm going to write the equations. So time starts, let's just move this. And let's move this. Okay, so now the model starts in 2024 and has a time step of 0.25. So I have time here in years. So let's put that there in the units. And I'll take the initial time is going to be here, initial time. And then the second step will be the initial time plus the time step. And I will anchor that. So now I have the first time step, and then I have the initial population here. So I'll just go down to the initial population, and then I say that the equation here is the population in the previous time step plus the births minus the deaths times the time step, and I'll anchor that. And then I'll calculate the birth rate. So this is equal to the population times the birth rate, and I'll anchor that. And I will divide that by 1,000. And then I'll calculate the deaths. So that's equal to the population times the death rate. And I'll anchor that. And I'll divide by 1,000. Okay, so now I have the births and the deaths. So let's copy this. And then I can continue copying it down. So I can take these columns. Oops, sorry. I can take those columns and I can copy them and I can run them down and paste them. And then you can see how the population is growing. And let's stop it at 2050. I think I have a problem here. I guess maybe that. Just check this. Oh, that's should be the crude birth rate here. So it should be 4, and then up down here. And then I can graph it. So if I graph population, the curve like this, that's 2100, but we only really want to 20 from 2025, let's say, to 2050. So there's the graph. There we have the graph, and this would be the same exact numbers as the Vensim model. So if we look at the model here and look at the graph, we see we get the same graph exactly. And we can look at the table of values and see that we have basically the same numbers, 200, 2.33 times 10 to the 8 units. So if we go up to 2050, we have 3.995 times 10 to the 8. And if we go in the Excel file, we can go down and see that we have basically 3.99 times 10 to the 8. That's the 2050 population. Okay, so that's what I want to show you today for how I'm modeling. And let's get back to PowerPoint presentation. So we will now go back, and as I said, there's the model, the stock and flow model, and then I challenge the model. Let's go back here and then next slide. So there's the model, and I challenge the model. So I ask it to critically review this model and identify the main errors, the main weak assumptions, and the missing feedback and required improvements. And this is what I got when I challenged the model. So I have these issues, I have an assessment, and I have a recommended action. So it says the stock and flow structure is correct, so we retain it. The birth feedback loop is correct, it's reinforcing loop, so we retain it. The death and feedback loop is a correct balancing loop, so we retain it. The birth and death rates are held constant for the entire simulation. So they clearly state this assumption or introduce time-varying rates. Migration is excluded, age structure is excluded, validation, there's no historical comparison, and policy relevance is very limited. So this is a challenge to the model. So so I would want to retain some things, but change some other things, and eventually get to a model that is perfected. So AI can get confused. So as we're making changes, it can get confused. So it may suggest changes that do not work, and it may create new errors while fixing others. And this can waste considerable time. So you have to test every change. Do not assume the AI is correct. So it's not perfect at doing systematics, so you have to be an evaluator of the work of AI. So I asked AI to assess novelty in this model, and I asked, could this model support a publishable journal article, identify the original contribution, the major weaknesses, the evidence required, the suitable journals. So I asked ChatGPT, could this model provide the basis for a journal article? And it said no, not in its current form. The model is too elementary to support an original research article. It produces the standard population identity. Population change equals births minus deaths with fixed crude birth and death rates. This is useful for teaching systematics, as I did in my textbook, and demonstrating exponential growth, which I did, but neither the structure nor the result is novel. It could become publishable if it was expanded around a substantive research question about Nigeria's demographic transition and tested against historical data and established demographic projections. So then once I've perfected a model and I think I have something that's publishable, then I get it to help me with the writing of the paper. And I get it to help me with an abstract, the introduction, the literature review, the method, the results, and the conclusions. And then I also, this is a basic format for a journal article. And then I have references, obviously. And then I put in appendices. I put in supplementary appendices with a causal loop diagram, the stock and flow model, the equations, the parameters and their source, the validation, and the baseline results, and the policy runs. So let's take a look at that. So I'm going to stop sharing, and I'm going to pull up a paper, a recent paper that I worked on, and just show you what it looks like. So let's, I'll share my screen here again. So here's a recent paper that I've been working on something called the hospital doom loop. And I got AI to help me write the abstract and the introduction, the literature review, the method, the baseline results, the policy runs. So I have various policies and I have some results in tables. I have a discussion and I have a extensive discussion. I have a conclusion, short conclusion. I have the references. And then I have the online appendices, supplementary appendices. So here's the causal loop diagram with the causal loop table. And then there's the stock and flow model with the Am I sharing my screen? So I have the stock and flow diagrams here. I have all of the different views from the model. You can see this as a complex model. I have the equations, and there's over 100 equations here, but it's all there for transparency purposes. Then I have the parameter sets with the variables and units. And then I have the validation that I did with the help of ChatGPT. And then I have the policy results, and I have various results, graphical results of the policies. And so anyways, that's a paper that I've been working on with the help of ChatGPT. So let's go back to my presentation. So let's talk about Nigeria's population growth as a more extensive model. So Nigeria's population growth has created a long-term planning challenge. So Nigeria's population has grown rapidly for decades. Fertility is declining, but remains above replacement. Life expectancy is increasing. Population growth may continue long after fertility declines. So we ask, when will Nigeria's population stabilize, and what pressures will continued growth create? So here's the historical timeline from 1950 to 2025, and we can see that we have exponential growth here. And then we can look at the birth and death rates, and we see that both the birth and the death rates are declining. I think that you might be able to see that the birth rate is declining faster than the death rate. So here's the migration rate, which is kind of minor, but there was a major spike in the early 1980s, possibly caused by a coup d'etat. And then we have a simple model that we've already seen, which is basically population with births, deaths, and migration this time. However, we have constant rates in this model, and we were told that that was a too simplified approach. So I generated a new model with time varying rates, and each of those time varying rates is a goal gap model. So I have a long-term birth rate, and I have an initial birth rate, and I have a time to change the birth rate, and I have the time to change the birth rate. So over time, the birth rate changes. Over time, the death rate changes. Over time, the migration rate changes. And that leads to births, deaths, and net migration. So the Venn-Sim model was replicated in Excel, and we had the same stock and flow logic implemented in Excel. We had historical data were used to calibrate key rates. The spreadsheet makes the model more accessible to users. Here's the spreadsheet conversion. So you see we have each row is a year of the simulation, with a time step of 1 year. And then each column is a variable. And we show here the population as a stock, birth rate as a stock, and so on, all the different rates. So, and the births and deaths and migrants. And then we have historical analysis. So we calibrated the model to historical data. So we see that we have a fit with the model in the Nigerian birth rates. So the long-term birth decline was captured, and the death rates and the death rate historical decline was reproduced. And the migration rate, the broad pattern was represented, but short-term volatility remains in the migration rate. And then we look at the historical population, and we see that the model with the calibration replicates the historical growth. And so historical fit is necessary, but not sufficient. And we look at the birth rates and death rates converge slowly. So we see the birth rate up until 2025, and then a continued decline in the birth rate. And we see the death rate declining for a few years, and then starting to increase as the population ages. And around 2117, the birth rate and the death rate intersect. And after 2117, there's more deaths than births. So population continues to grow while the birth rate remains above the death rate. And then we can look at the population over time, and we see that population is growing exponentially here, and then there's a diminishing rate of growth. Eventually it peaks, and then it starts to decline. So that's my population model for Nigeria. So the conclusions are that population growth continues for many decades. Population model projects that there's going to be a peak around 2117. The demographic momentum delays stabilization, and continued growth increases pressure on infrastructure and public services. This is a projection. It's a scenario, not a forecast. I just want to make that clear. So now I'm going to get into something that may be more interesting for you in space leadership. And that's something called the Kessler Syndrome. And the Kessler Syndrome is a situation where more satellites create both value and collision exposure. So satellites launches increase operational capability. More active satellites increase collision exposure. Collisions generate additional debris. Debris increases probability of future collisions. And the central question is whether the system contains a self-reinforcing debris mechanism. So here's a simple causal loop diagram with a reinforcing loop over here showing that collision exposure, you have active satellite losses, and that leads to debris, and debris leads to collision exposure, which leads to more active collision losses. We have active satellites lead to collision exposure, lead to losses, reduces active satellites. We have active satellites leads to satellites and reaching end of life and reducing active satellites. So we have two balancing loops and a reinforcing loop. And the question is, which is the most important? Is it the balancing loops or is it the reinforcing loop? And we can only answer that by building a system dynamics quantitative model. So here's the quantitative model. We have launches per year growing over time. We have a growth rate, and then we have satellites. So we have launches, and we have satellites reaching the end of life, and we have satellite collision losses. We have collision avoidance, and then we have debris, and debris leads to more collisions, and then collisions lead to more debris. So we have this loop here of debris. Anyway, so that's the That's the stock and flow model. So if we look at the parameters of interest for governance, we have growth rate and collision avoidance. And we compare 3 different scenarios: business as usual with a growth rate of 3% and a collision avoidance of 90%, weak governance with a growth rate of 5% and a collision avoidance of 80%, and a responsible growth with a 2% growth rate and a 97% collision avoidance. So business as usual eventually reverses satellite growth. So here's the picture that was generated in the business as usual case. We see that we grow quite substantially, but around 2050, we end up seeing a decline in the number of satellites created by collisions. And the active satellite population begins to decline after collision losses increase. And then in the weak governance, we see a rapid system failure. So here it suggests that the business as usual is in blue and the weak governance is in red. And we see that we can end up with a drastic decline in the number of active satellites because of collisions in space. And then so faster launches cannot compensate for deteriorating collision conditions. The last scenario is responsible governance, and it sustains satellite growth. So here we have the 3 scenarios, and we see the green one of responsible governance. The growth continues well into the 2050s. So lower launch growth and stronger collision avoidance can preserve long-term operational capability. So here's the debris. You can see that debris accumulation is difficult to reverse once the reinforcing loop dominates. So we can see the weak governance. The amount of debris is very large. In the business as usual, it's also starting to grow. And then in the responsible governance, it looks like it's very small. So governance determines whether growth remains sustainable. So launch growth initially increases operational capability. More satellites also increase satellite collision exposure. Collisions remove satellites and generate debris, and debris creates additional collision risk. And weak governance favors short-term growth over long-term viability, and responsible governance reduces the risk of systemic decline. So feedback thinking turns model results into strategic action. So systems are shaped by feedback, accumulation, and delay. Causal loop diagrams explain why behavior emerges. Stock and flow models can test how systems behave over time and how behavior changes. And policies must be evaluated for delayed and unintended effects. And AI can accelerate analysis, but cannot replace modeling judgment. Space leadership requires attention to long-term system viability. So applications for space leadership: strategic planning, policy design and testing, capability development, risk and resilience, stakeholder alignment, technology investment decisions, and the using models to expose assumptions before the assumptions become commitments. Recommended resources: here's some books you can look at and websites. The Nello Meadows book, Thinking in Systems, is very good. And then Peter Senge's 5th Discipline is very good for causal loop diagrams. And then John Sterman's book, Business Dynamics, is basically the System Dynamics Bible. It's a major textbook in the field. And you can look at my little textbook called System Dynamics Modeling and Simulation with Excel. And you can look at the website called the Systems Thinker, the System Dynamics website, or the Waters Institute for Systems Thinking. My final thought is, where could feedback thinking and carefully governed AI improves your decisions. Thank you for your attention. I open the floor to questions and discussion, and you can always reach me at ivan@policydynamics.ca. I'm available on LinkedIn, so we can connect there as well. Thank you very much. Hope to talk to you again in the near future.